Thank you. Thank you very much for the organizers, and thank you for the opportunity to meet old and new friends in this wonderful conference. So I'll be talking about some of our work on superconducting quantum optics. And this is done at the Hebrew University in my lab. But before I start with my stuff, I want to say the more official Mazal Tov to the Bar-Ilan Center under my role and hat as the director of our quantum center at the Hebrew University. So we welcome this new center and think it's a wonderful thing that this is rising to a new level of collaboration and connection in Israel and worldwide. I prepared too many slides, but I hope to give you a feeling of what we're doing. And again, this is, as Roy said, this is mainly the work of students and postdocs and collaborators, which I want to acknowledge and happily thank them for all their discussions and help throughout. Of course, funding is very relevant and important all along the way. As soon as you start pasting in more and more pictures of people, you know that it's time for a new group photo. Most of the people here are alumni, but I want to point out especially Elisha and Naftali, whose work I'll be showing today. Elisha is in the audience somewhere, and if there's anything you don't understand, then we can probably both try and answer it. So this is the big picture of our work. Of course, there's a fabrication effort to make the devices, and once they're made, we measure them either in quantum optical contexts of, say here, Wigner function measurements. I'll be showing some of that later. Coupling to atomic systems. Here's an individual atomic system oscillating in and out of coherence with a macroscopic electric circuit, and also some more many-device, many-level quantum optics experiments, and I won't be talking about our laser spectroscopy lab at all today. So the outline. I'll talk about our project for quantum walks in superconducting networks, quantum classical transition in nonlinear oscillators, phase-based tomography related to the second topic, then shift gears to looking at more deeply at the actual superconducting solid-state aspects of coupling to individual defects and the intrinsic nonlinearities of superconductivity in this context, and some very recent results from yesterday that were mailed to me by the students who are happily working away at the lab while I enjoy the conference here. Some amplifier results at the few photon level, and hopefully we'll get to our Pythagorean and Dirac particle emulation results and proposal. So that's a lot of work, and we should get started. So the quantum walks on a graph is a project in which we're attempting to look at a very, very simple system, probably the most simple many-body quantum system you can imagine. It's bosons. They're connected on a graph. Coherently hopping, no interactions, just particle statistics. It turns out that this problem for fermions is easy. It involves evaluating determinants. For bosons, at least in the asymptotic limit, it's considered a hard problem in the context of computer science. Due to bunching effects, you need to calculate a permanent, and that is known to the third asymptotic level by Scott Aronson to be a hard problem. So what does it look like in our context? We're talking about superconducting resonators coupled. Here, for example, we called it a quantum harmonica, but it's not really quantum in this experiment. We were driving it with coherent pulses, but regardless, you have a bunch of resonators coupled between them with both long range and nearest neighbor. Here, with just nearest neighbor, if you insert a single photon, or a coherent state actually, into one of the sites, it coherently sloshes, and you get this famous linear expanding lobe versus the classical diffusion equation. Here it's coherent diffusion. So this is the single particle behavior, and it gets complicated when you start adding more particles as their initial state. The interference effects are intrinsically quantum, coming from the particle statistics and the complexity driven by that. So specifically, the proposal which we're building, or trying to, involves these resonators, the blue resonator sites, a coupling, black capacitive coupling network, qubits to drive single photons coherently coupled into the resonators, and then allow them to slosh around in the blue and black network, and then extract them using the qubits as single photon detectors. The qubit is a very high efficiency single photon source and a very high efficiency single photon detector, which is sort of one of our added values compared to optical photons, where the single photon source is still a challenge, especially in terms of integration. So this is what it looks like schematically, and then going to the fridge level, you would have some sort of box with microwave lines going down and amplifiers chained to multiplexly drive this whole story. Just to introduce our main players in this context, we're talking about superconducting coplanar resonators. These objects here, for example, from the Yale sort of style, these objects are basically coax folded it or sliced it into 2D. And here's a launcher pad, here's a feed line, and here are capacitively coupled resonators. These are lambda over 2, I think, resonators. I can't see the termination, it's not in the photo. And in terms of resonator theory, this is a very simple object. You have a feed line, there's an internal quality factor, a coupling quality factor, and usually you want to operate it when those are roughly equivalent. That's your best signal to noise in that context of driving and readout of the resonators, but some other regimes are, of course, relevant. Now, for example, the harmonica I mentioned before had 88 resonators on a chip, on a 6mm chip. They were coupled in a complex pattern. They also had different lengths, as you can see here, which generated also a frequency ladder aside from the coupling. And then the coupling, the gaps here are not noise. They are actually a fractal sort of structure which emerges from the band interactions. And especially dramatic over, it's hard to see here, but over 2.5 decades, the coupling Q, which is the coupling to our feed line, changes dramatically as you go to different resonances, because we have resonators, but when they're all coupled together, it involves complicated modes, which some of them have a symmetry which is not driven by the feed line. So you get very, very high coupling Qs, indicating that it's just very weakly coupled to the feed line environment. Now, we've also been working, and I'll show some of this later, on some newer fabrication tools, including crossovers to go to, say, 2+1D geometries, allowing us to get these more complicated coupling networks. We're also looking into flip chip technologies in order to increase the bias control. These devices were fabricated at our Nano Center by the grad students and postdocs. This is a resonator feed line and 8 resonators multiplexed off of it, driven in a material which is dramatically different from standard superconductors, in the sense that it has a very, very high kinetic inductance. I'll define this later. Mainly, it means it's a very, very poor conductor at room temperature, and the resulting wave functions are extremely not non-plane waves, not localized, but not plane waves either. So looking at the theoretical numerical analysis of the quantum walk proposal, we can plug in the numbers, the known numbers of superconducting devices, and see that our proposal is actually quite realistic in terms of going post-classical, or the buzzword quantum supremacy is sometimes used, in the sense that with known lifetimes, we can solve out to, say, 5 or 6 particles in a 10-site network. After that, it crashes the laptop trying to simulate it. And you can see that you're getting pretty mild decoherence effect, even in rather large Hilbert spaces. We're talking about a Hilbert space of order a few tens of thousands, even 100,000 states involved. Now, maybe a little more subtle and interesting is to try to distinguish between coherent effects having to do with, for example, what would happen if you would input coherent microwave pulses with an average energy of 1 photon and compare that to the single photon interference effects, trying to distinguish between classical interference and the more rich and larger Hilbert space of quantum interference. And here we're showing that if you look at the proper measure in your output, then you can start distinguishing between Fock state inputs and coherent state inputs. And as the system gets larger, the distinguishability becomes larger, and it would be interesting to see if this crossover really makes it ultimately truly distinguishable between quantum and coherent effects. There is always going to be some overlap, but do these lobes become completely separated ultimately? And that's as far as we know, still open. So let's zoom in on a single device and try to understand more carefully what is quantum versus classical in the response of such a system. So just to be more concrete, what are we actually measuring? So this is sort of a fridge. That's a sample box. There's a chip. That's two coupled qubits. Zooming in on a specific one, this is a phase circuit, mainly because it gives you a huge advantage in being able to measure the occupations of all levels out to tens of levels. Sure. Oh, that's probably the question was, how would you prepare a coherent state? That's probably even easier. What you would do is actually if you drive with a strong enough classical coherent pulse, you can ultimately excite the resonators directly. Yeah, just apply a coherent state to excite it. That you can calibrate within the system by just driving a coherent pulse. So the qubit would be excited at its resonance, but you could drive the resonator directly. So this is sort of zooming in on the system. Here's a Josephson junction. That's a top electrode. That's a bottom electrode. There's a oxide barrier here not resolved with nanometer thickness. So the Hamiltonian of such a system in the classical limit is just like a pendulum to a certain extent, at least at lower energy excitation. And this sort of nonlinearity has a softening branch, which leads to 2 metastable branches, which you can climb up if you go adiabatically from the high frequency to the low frequency. And in the classical sense, this sort of adiabatic chirp, going from high frequency to low frequency, is a control that here it's parameterized by the anharmonicity of your system in the quantum limit and the rate in which you're chirping the drive. And there's a crossover in which, if your amplitude is large enough, you can stay latched onto the higher branch. If your amplitude is too low, as you try to cross over the linear resonance, you're going to drop down rather quickly into the lower branch. In the quantum sense, if you start quantizing things and looking at a larger anharmonicity, the threshold, again, has a different behavior. But let's start with a simple experiment in which we chirp our drive and subsequently measure the populations in the system. Here in the semi-classical limit, we see a wave packet. We never excite a single state. We see a wave packet that is continuously excited out to I don't know, 15, 20 levels of the weakly anharmonic system. So this is a nonlinear oscillator which is being phase locked onto the drive to excite it out to the bandwidth of our drive. And in Wigner representation, this looks like this. And these sloshings that you see here are because we didn't have enough bandwidth to turn it on completely adiabatically. But ultimately, it latched on. It started out not quite adiabatically and went up high. This is actual data. Again, as a function of time, we do very well-defined population tomographies. In a quantum sense, you have, in the reference frame of the drive, you have, so here's the rotating frame. It's a detuning scale, energy. These are the instantaneous energy levels. And it becomes a question of whether you're adiabatic or not, especially on the first crossover, because that's the smallest one. After that, the crossovers become steadily larger. So if you got through the first one, you'll get through the rest. And it's analogous to the classical one, but because of Landau-Zener physics, the threshold is different. So here's the data, and here we're only going out. We tune the system to much larger anharmonicity, and when we chirp, and these oscillations, if you can see them, are real, representing, again, some mild non-adiabaticity. And then we excite it out to the fourth or fifth level as a ladder climbing phenomenon. Now, mapping all the data we took onto a phase space of anharmonicity versus chirp drive normalized by the strength of the drive versus the chirp strength, we get a phase space representation showing that in the classical regime, below the blue line, in the sense that we're exciting wave packets, semi-classic wave packets, it's called autoresonance. It's a classical phenomenon of phase locking in nonlinear systems. And in the more quantized regime, we have a Landau-Zener threshold behavior which scales differently, and this is the data. Compare it to simulation, no fit parameters, it looks okay. Now, relating to something that maybe Klaus was talking about yesterday, we can drive our system into a metastable state in which the actual ground state is this sort of locked wave packet, and it's self-stabilized with its environment. You can think about it in terms of environmental engineering in the sense that when you latch during the chirp and go up to the high frequency drive, you end up with this sort of wave packet sitting in a quasi-potential given by the detuning from the drive. But ultimately, it tunnels out through the corners of this crescent and spirals down into the true ground state. And that can be understood in terms of a holding experiment in which we show that after you chirp, you can hold it with a different strength of drive, static frequency. You can hold it exponentially longer in this stabilized wave packet. This is interesting for sensing because it extends the lifetime, and the tunneling effects can be related to a temperature. So any fluctuations, in addition, happening while you're trapped up there can be thought of as your signal, and ultimately is something you sense. So I showed some simulations of phase space tomography, and that, I want to define that better. That's the Wigner function. And the Wigner function is an object defined as the autocorrelation of the Fourier transform, the autocorrelation of the density matrix of the state. So the single mode Fourier transform just talks about quadratures. Yesterday, in a beautiful talk from the PL group, we talked about the X and Y, or I and Q quadratures of a single mode. So here, again, are the standard Fock states, coherent states, which the ground state is the only one common with Fock state, no photons, but then displaced photons with a certain amount of phase and energy. And of course, superposition of Fock states have interesting symmetries related to the phase between the two Fock components. So we'd like to measure the Wigner function of our device, of our system, and that can be done by so-called displacement tomography, in which you apply a displacement and just measure the populations And that turns out to be, the parity of those populations turns out to be the Wigner function at the displacement. This is a well-known result from quantum optics, adapted to superconducting networks and devices in the Martinis group. And the displacement is just the area theorem integral over your Rabi frequency. But we want to displace an anharmonic oscillator. So the trick we find is to tune it to be weakly anharmonic, and then apply a very short pulse. That involves some getting your microwave pulses to be so clean and nice that they're just 1 nanosecond or 2 broad. And then the system within the relevant manifold responds quite harmonically to your drive. Measuring the populations on that will give you the Wigner function. But how do we generate? Now we've shifted the problem. If we're measuring it as a harmonic oscillator, we know that harmonic oscillators are not the best systems for quantum control. You can only get coherent states with classical drive. So we've shifted the problem to the problem of controlling a very weakly anharmonic system, and you want to do it with a short pulse. That thing is still on. Now it's not. Thank you. So how do you control a weakly anharmonic system? Well, our answer was evolution. At least in our lab it works, and probably also in nature. So that's a good thing. Well, in America it's controversial. When I say this in America, there's always someone who gets troubled that evolution actually works. Anyway, so you choose an arbitrary amplitude and phase for whatever sequence, and you call that a genome. You start out with a gene pool, and this is a standard procedure of genetic optimization in which you breed, measure a fidelity of how successful a particular genome was, and you add noise and feedback on that. And here, for example, we were shooting to excite the fourth level with high fidelity, and this was done in just a few nanoseconds. Whereas the Fourier limit, if you were trying to design a sequence just based on your intuition of Rabi, would require probably at least 10 times that, and within our decoherence of this circuit, that would be impossible to reach these fidelities. You can also do superpositions. The genetic algorithm converges a little slower, but gets a very high fidelity for superpositions. And now, of course, once you have superposition states that were your target, you can Wigner function them, and this is the data here, and that's the simulation with no fit parameters. So we were just designing, we told the genetic algorithm, design this sort of superposition, and then do its tomography. You can represent that in harmonic basis. And once you have this sort of method, you can look at more interesting states, such as what happens during our chirp, and actually see these crescent wave functions coming out of the data as you excite it. And then when you turn the drive off, they stop being localized, immediately disperse, and then eventually collapse back down to the ground state. And of course, this can be also represented in the harmonic oscillator basis, and you see that the dispersion just changes the phases, but ultimately decoherence brings you back down to the diagonal. You can look at the purity of the system, and it really matches our simulation very nicely, going from the chirp to a dispersion and then to decoherence, bringing you back down to the ground state, which is pure but boring. So I mentioned, aside from quantum optics on that level, we also use the superconducting circuits, which are large objects on the order of tens of microns, to couple to atomic defects, either within the junction or on the surface of our system. So this is by now a quite famous slide in which we measured, as a function of bias, changing the resonance frequency of the qubit, we measured avoided level crossings in the spectroscopy, and in the time dynamics you see you can excite a single photon into the electrical circuit and see it slosh back and forth coherently from an atomic system. And it took a while, starting in the Martinis group during my postdoc, and then subsequently in joint work in my lab. It took a while to figure exactly out what was going on, and some effects are still not understood, and there's a lot of work going on also at Karlsruhe. related to this. Now, specifically, if you zoom in, the model is that of we start out talking about a universal model of uncoupled two-level systems related to some defect dimension in which there's an energy mismatch between two wells and tunneling. And this is in actual physical space, not in some abstract phase space. These are actual defects in the amorphous oxide, say, within the Josephson junction. And the electrical field from the large oscillations in the circuit is coupled to the dipole moment of such transition between the excited and ground states of these defect states. The coupling strength can be associated with the tunneling. That is proportional to the dipole moment, and there's an angle, eta. But ultimately, you're going to see a splitting in your spectroscopy, which is given by this sort of form. And so that's about a nanometer. And this is the gigahertz frequency of the oscillator and the capacitance, translating basically a photon into an electrical circuit. That's what you have here. So it's really a dipole moment calculation, and once you know that, you can apply various swap experiments to tune either coherence or population into the defect and measure its lifetime and coherence with these nice protocols. So you transfer coherence into the atomic defect and then beat it against the local oscillator and the coherence on your qubit, and you see a decaying signal indicating the coherence of the actual atomic defect. So this is the first time such things were accessed at the microwave frequency at the single defect level. And if you measure about 100 of these, you can start getting statistics showing the lifetime and coherence of the defects. This is a main decoherence bath for the superconducting circuits, and understanding these mechanisms related to phonon relaxation and also spectral diffusion are still of interest. There's also some temperature data we took, which is relevant as well. Now, the harmonica I showed earlier was a little too complicated for us, and we said, let's back off and measure individual multiplexed resonances and see how that behaves. And what you see here is at well-defined frequencies with dispersion of 10 to the minus 5 from where we planned them to be, we get resonances which we can access, again, in a multiplexed way via this central feed line. So it gives you a lot of statistics to measure things either simultaneously or just individually. And you can get coupling Qs and internal lifetimes which change as a function of power. This is a saturation mechanism. You're driving just here a linear resonator, and you're changing its Q factor here by almost an order of magnitude in certain devices. But we wanted to understand the decoherence mechanism a little more carefully, so we built this dimer. So it's a coupled oscillator. This is probably the first thing you do, or second thing you do in a first-year undergrad lab. Take two coupled oscillators, and you get coupled modes, an anti-symmetric mode and a symmetric mode, which we observe both of them from our feed line. And then you can pump and probe on either one, and that sets up a more careful distinction between saturation and resonance to measure them more carefully. So what does it look like? We have these X's mark spatially random two-level defect states on the surface or in the interfaces of the resonators. And we have a symmetric mode and anti-symmetric mode, and they're spatially identical. So they're very complicated fields given by elliptic functions on the coplanar waveguide, but they're completely overlapping everywhere in space except for the coupling region, which is small. So it's about 1% of the energy. So everywhere else, the fields are completely mode matched because locally, you don't even know whether you're in the anti-symmetric or the symmetric mode. You just see it by frequency. So just looking at the single resonance driving a mode, we see that it's very, very flat in its response over about 6 or 7 orders of magnitude in power. And then eventually the frequency starts shifting in a dramatic way, which I'll explain in a moment. The loss tangent, which is 1 over the internal Q factor, improves dramatically, but only by a factor of 8, even though you've changed the power by 7 orders of magnitude. This is something that no one understands. Now, shifting to the pump probe experiment I described, you see something a little different, where it depends where you're pumping. You see a frequency attraction. So suppose I pumped on the blue resonance, then you see the frequency shifts down. And if I pumped on the green one, the frequency of the probe shift goes up. And then ultimately, at high power, you always get a downward shift in frequency. So this behavior is something we wanted to understand because it really puts the finger on the nonlinearities and the loss and the saturation more carefully than just the single mode drives. And, well, let's skip that. And the mechanism we proposed, which was ultimately analytically solved by Sasha Burin, was to say that when you drive in this coupled mode system, you saturate locally, and that opens up a window of saturation that the other resonance feels both as a sharpening of the mode, but also as a frequency shift because of avoided crossing off-resonant shifts. So when these guys are saturated, they don't push on this resonance as strongly, and you get a lowering of the frequency. It would be reversed if you were pumping here and probing here. And of course, if you drive really, really hard, eventually it symmetrizes everything, and you stop seeing a shift. So these are the analytical expressions solving this pump probe experiment, and it really matches what we see. The fits I showed earlier were there. Now, it's important to realize that this is a very complicated system. There are millions or even billions of two-level defect states in a highly inhomogeneous field. Some of them are saturated very quickly. Some of them are hardly saturated. And it turns out that if you solve for the inhomogeneous fields, you can really understand where the decoherence is going on and try to improve your devices. And we did that, and we can distinguish between homogeneous, uniform field models and non-uniform models. And we can say exactly what is the single photon Rabi frequency to coupling to individual defects, which we can almost resolve in this experiment. So, what's going on at the high power? At the high power, there was always a lowering of the frequency. What's going on there? And the high power is the kinetic inductance regime. For those of you who don't know what kinetic inductance is, it's something that is not usually taught in theory because it's a beautiful experimental effect. Kinetic inductance is the energy associated with the kinetic energy of the charge carriers. Now, when I usually talk about inductance, I usually associate the prefactor of I squared, the current squared, with a magnetic field. And this is true to within 10 or 12 orders of magnitude in normal metals, except at extremely high frequencies, maybe terahertz frequencies, you start seeing the kinetic inductance coming in. But at gigahertz frequencies and lower for normal metals, the kinetic energy of the charge carriers is completely negligible. That's not true in superconductivity. Superconductivity, you have a lot fewer charge carriers going much faster. So the kinetic energy is much more important. It's still negligible in standard BCS superconductors, but when you go to highly amorphous superconductors where the wave functions are more localized and the BCS still applies, but with wave functions which are far, far from plane waves, you get very strong kinetic inductance effects. So when you drive a current through this material, the kinetic energy of the charge carriers can be 50 times larger than the magnetic field generated by that current. So it's a big effect in these materials. So even in our aluminum oscillator, resonators, it's about a 1 or 2% effect instead of 10 to the minus 12. And when you plug it in this sort of model, you get something which raised a smile on my face because it reminded me of my good old days when I was a grad student with Neil, looking at Bose-Einstein condensates and the wave mixing effects that occur there. So it's a Kerr nonlinearity, and here we're looking at 2 modes. And of course, there are beautiful extensions, 3 and 4 modes, mixing the 2 boson fields within these resonators. And it looks like this. And the important thing is to distinguish, if you pump on one mode, you get twice a shift on the other. This is the Heisenberg equation of the operator. You see the frequency change. You're doubly sensitive. If you pump on one, they have to share the same space. So the nonlinearity of the kinetic inductance is mixed in. And this is a theory which was initially proposed by Eyal Bux a bit more than 10 years ago for a single mode. We adapted it to the 2-mode representation and were able to explain our shifts and determine that the nonlinear coefficient for the aluminum we were using was 10 to the minus 4 hertz per photon. And that's, I don't know, is it precision or accuracy? That should be compared with the 10 to the 10, roughly, hertz of the resonance. So it's 10 to the minus 13 distinction in scales here. Is that precision or accuracy, Lloyd? Who knows? We'll think about it. Now, the nonlinearity becomes important.
Can one calculate it?
Yes. Yes, you can try and estimate it. It's related to a pair-breaking current associated with the critical current of the device. And that you can, of course, control if you go to smaller dimension constrictions. And this nonlinearity goes through the roof. And I'll show in a minute, something like that. How much time do I have? 4 minutes. OK, let's move faster. So can we amplify and modulate with this system? It turns out we can. This is a device which is now in the fridge. That's a cartoon of the device. This is a zoom on the device. You design a 1D crystal with the appropriate band periodicity, and then you can phase match over almost a whole decade of frequency. And this is preliminary data. We engineered the band gap to be at 5.8 gigahertz. And then when we pump and probe, we see our idler signal. There's a signal which is being mixed into an idler, and it goes up and up as the pump is increased, indicating amplification as expected. Of course, we need to work on the impedance matching and look also at DC bias, in which we'd get a more efficient and smoother three-wave mixing performance. This is the first traveling wave amplifier, as far as I know, in Europe and Israel. It's an American technology which is first time successfully implemented in a new material here in Israel. So we talked about single devices. Let's start coupling at least 2 qubits to see what happens. And this is an interesting system. But it also is related to the 4-level system in a single device. And there turns out to be a beautiful mapping between the two, which was, I should say, rediscovered because it has a long history. But it was really brought to the fore by Chaim Sukowski from Tel Aviv, who really elucidated this connection. So you define 2 fictitious qubits which map to a 4-level system. And then in the Hamiltonian, in which you just have these sort of drives, you can map it into 2 independent qubits driven separately with the appropriate dressed Rabi frequencies. So you have a lab frame. This is the actual experiment you do. And this is the mapping you do in order to understand what's going on. And these independent qubits have beautiful mathematical connections between their Rabi frequencies. And if you tune the drives to be a Pythagorean triplet, you can get a nice population inversion from 0 to 2 here with high fidelity. And that's called Pythagorean coupling. And here's an experiment in which we parameterize our drive strength by P and Q parameters. and we scan P and Q, and we see the resonances coming out exactly where you expect them. So this is the data here, and it's where you expect them at low powers. And when you go to high power, something really dramatic is happening. And here's the Pythagorean as a function of time. You really see you're matching. These are odd integer rational ratios, and it really adds up. So what's going on? We realized, we called Chaim up and said, your theory's good at low power, what's going on at high power? And we realized that there's a subtlety to our particular Hamiltonian. He was right, of course, if there were no detunings. And when you add the detunings in, you get an effective Cartan decomposition and a high power mixing between the qubits. So you can think of it as a coupled qubit experiment in that basis. So really the two mechanisms are interfering, and that's the data we see. So I'll have to really rush through the last part because I stand before you in dinner or lunch, so you might end up eating me. So the bottom line is that these four-level systems can also emulate Dirac particles. It's the same Hamiltonian, but there's a bunch of subtleties having to do with the representation. And in the end, we found something that Elisha discovered, also related to his family background, speaking to his parents. And he found that the supersymmetric representation is the natural way to view this four-level system. And we can actually solve Dirac dynamics in the internal spinor basis. That's an interesting simulation platform. And it's really quite ideal for Josephson circuits. So what we need are two coupled qubits. There's a nice analogy, which I don't have time to show, to dark states, explaining the oscillation dynamics. So we actually separate the manifold into two degenerate bright and dark state systems. And you can look at the helicity. But the exciting new part is you can add a chirp, and that is a high energy experiment in the sense that a chirp on these Rabi frequencies is an electric field. And that relates to the Schwinger pair production mechanism in the first quantized basis. Again, a quantum optics analogy of that is a degenerate, four-level degenerate Landau-Zener transition, where we see as a function of your mass and your chirp, you can see a crossover into pair production. So that was a bit fast, but ultimately, I hope I gave you a picture of how quantum optics has a new friend, and the new friend is superconducting circuits. And we're happy to share and talk to our more senior optics friends, and ultimately learn new things. So it really is an exciting time. It's not just a quantum computing platform, it's an incredible quantum optics platform. It probes fundamental superconductivity from the solid state perspective and couples to spins and ions in an exciting way, which was not possible elsewhere. So thank you for your attention.